Okay, so this is our kind of first introduction to Unit 5, and so we're going to talk about intermolecular attraction forces. And so I know I briefly talked about this before, so part of this is going to kind of feel like review, but I want to make sure that you are solidified on your thinking when it comes to intermolecular attraction forces, and then talk about it in a little bit more depth. So recall that intermolecular is molecule to molecule. So we're not talking about intra, which is atom to atom. We're focusing on how one molecule attracts to another. And we have to recall that the strength of these forces really depends on their polarity. So there are a couple things that governs the strength of intermolecular attraction. And just remember that I like to abbreviate this, the intermolecular attraction forces, as IMF. So if you see that, that's all it means. And so what it's governed by, let's start off with symmetry. When you have a symmetrical molecule, they're going to have equal electron distributions. And this is throughout the whole entire molecule. And this leads to them having weak intermolecular forces and tend to be gases at room temperatures, as they don't want to stick together, they're not attracted, so they easily slide past each other into space. And so one thing to note though, and this is kind of going to be a theme, is that the larger the nonpolar molecule, they're going to have higher intermolecular forces. And so these tend to form volatile liquids, just meaning that they like to evaporate, or waxes. So if you recall the lab that we did on testing if things are conductors, did we have a wax? Yeah, so that was just a really big nonpolar molecule. And so the other thing we have to consider is electronegativity. And so when now you have an asymmetrical molecule, they have unequal electron distribution. And so this creates the partial charges we see. Because the electrons, they spend more time with the more electronegative atom. And so again, recall that when you have asymmetrical and unequal electron distribution, the electron spends more time with the more electronegative side and causes the charged ends to form, which is meaning we have our polar molecules. And so with those partial charges, would the more electronegative side get the positive or negative charge? Negative, because the negatively charged electrons hang out on that side. So just recall that. And so the stronger the polarity, or think of it as the electronegativity difference, you're going to have those stronger intermolecular forces. Those molecules are going to want to stick together more. And so typically these form liquids or solids at room temp. So you guys recall this information? It feels good? You're comfortable with the concepts here? Okay. And so we're going to kind of now give names to these forces that these different types of molecules have. And so we have London dispersion forces. I'm going to abbreviate that as LDF. And so these exist in nonpolar molecules. And what happens is there is no charged ends here. And so this makes it extremely weak. So it's kind of funny to call something attraction forces when there's practically none that exist. And so what causes these forces is there are temporary poles or charged ends that do form just from the movement of electron movement around the molecule. And so it's very brief that this happens, and it doesn't happen a lot, which is why they have weak forces. There's not much attraction that comes from this. Another thing to note, again, we have a larger molecule, then we have a stronger London dispersion force that happens. And so that's why I kind of pulled these examples for you guys. So think of each of these are just hydrogen gas, H2 molecules, and this is representative of the attraction. And so a way that we can kind of measure these attraction forces is the temperatures that they boil at. So notice now comparing between these two, how much does one hydrogen atom weigh according to the periodic table? About what? About 1, right? So H2 weighs about 2 atomic mass units. What about oxygen? How much does 1 weigh? So if you have 2 of them, it's about 32 AMU, right? And notice how we go from a boiling point of 20 Kelvin to 90 Kelvin. Now, the atomic mass of CH4 molecule is only 16, but it still has a larger boiling point because of the size of the molecule. Now we're getting to a larger molecule. So when you're comparing things that are just linear, totally okay to look at mass here, but now we're looking at size of molecule, which is giving this extra boost of extra boost of temperature that it takes to boil. And so you can think of it as more space for the electrons to kind of get stuck and lost in, and they're more likely to get tangled up and hang out in one spot a little longer, creating those temporary poles. The next we're going to talk about here is dipole attractions, and we've talked about these already too. Again, we're just giving a name to them. And so these exist in polar molecules. And so this is just defined as the attraction of a partially positive end of one molecule to the partially negative of another. And so if you look on the picture that I made to the right here, if we break it down to just one molecule here, we've got our one line of symmetry, it's polar. If we break down the electronegativity difference between sulfur and hydrogen here, sulfur has 2.6 while hydrogen has 2.1. Electrons want to hang out more towards sulfur. So this is what gives the negative charge towards the sulfur end, positive towards the hydrogens. And so when you bring another molecule in proximity, the partial negative of one sulfur attracts to the partial positives from the hydrogen from another molecule. Now we have to talk about hydrogen bonding. And so this is a strong bond. What happens is there's a formation of temporary covalent bonds. And all covalent is, again, just remember the sharing of electrons. And so the most notable molecule that does this is water. And so the difference in electronegativities between oxygen and hydrogen is strong. The difference is 1.3, but there's more than that that actually happens. And so the hydrogen from one molecule actually forms a temporary covalent bond with the oxygen from a different water molecule. And so the reason this can happen has to do with, one, oxygen has strong electronegativity, but really wants those electrons. But really importantly is its small radius. And so what happens is that it delocalizes the electron. And all that means is the electron's supposed to be shared in one spot, but it delocalizes it a little bit outside of where it normally exists. And it's shared, so it delocalizes that electron that's shared with the oxygen in the same molecule, causing it to simultaneously bond to both oxygen in its own and from another molecule. So again, explaining this concept now here with a picture is, so the hydrogen from one molecule forms this temporary covalent bond. So this is the hydrogen bond here. This is the covalent bond that exists between atom to atom, so the intramolecular bond. Here's the intermolecular covalent bond that forms. And so oxygen really, really, really wants that electron. So it delocalizes the electron here to simultaneously form a bond with both. And so this is just the scale between 3 molecules, but what it kind of more realistically looks when you have a bunch of water molecules is kind of just a random assortment here, where the oxygen or the bigger atom is attracted to the hydrogen of another. Any questions on hydrogen bonding? Okay. So this is what makes water water. Like, this is why water is so important, is its properties that it has a lot to do with the size of the molecule corresponding to how it interacts with itself. And so this is why there's such a high melting point, boiling point, heat of fusion, and vaporization for a molecule that's as small as water. And so this also gives its ability to form a skin. And what I mean is surface tension. So if you've ever seen a bug or something walk across a lake, it's because of the surface tension that water can form with itself. And last but not least, it also makes it able to climb up narrow spaces. So this is why plants can live. This is water climbs up the narrow roots of a plant to get to the leaves. It's because of these properties that life is as it is. And so if you think about it too, you guys see this in lab. When you measure water in a grad cylinder, what does the water do? Climbs up the edges, right? That's why we have to read from the bottom of the meniscus, is because it really likes itself. And so there are other atoms besides oxygen that can hydrogen bond. So all I'm saying is other atoms that are going to make those bonds are nitrogen and fluorine. Chlorine does not bond. And it's not a sense of electronegativity. It is very electronegative. It has to do with the extra principal energy level. So remember, as you go down the rows or periods of the periodic table, you're adding those layers, Shrek meme. And so as you add those layers, the radius gets too big, so it can't hydrogen bond. And so this table is a nice little summary of kind of what we talked about previously and today, starting with, if we have a polar molecule that hydrogen bonds, it's going to be a really strong attractive force, which therefore leads to a high melting point and its poor ability to evaporate. High melting point because it really wants to stick to itself, poor because it doesn't want to move away and evaporate. Dipole attractions in polar molecules. They're about middle of the road, so moderate melting point. They're okay at volatilizing. And then we have our nonpolar that shows LDF, which have a weak attraction force, low melting points, and are good at evaporating. Are there any questions on this content?